We're kind of on a bridge between 15.3 and 15.4. If you want, we can think about this as being in 15.3. So, this is the volume that we're looking at within here. So we can establish our f function f of xy is equal to the z is equal to whatever that is. And then, so we can imagine that this is going to be our integrand. So when we're looking for the volume, this is going to be a double integral over our region. And we'll talk a little bit about the region so that we can set up the integral. And then our integrand is x squared plus y squared. And when I write dA, just remember that this is a combination of d something and d something. And the order can be switched, so it depends on how you're going to integrate with respect to first. So that's the next thing we're going to try to figure out, is that this is our region that we're going to integrate over. And this looks like a circle, and well, with a circle, it looks like we can integrate with respect to either x or y first. So anybody have a choice? Integrate with respect to x first, and then y. So let's integrate with respect to x first. And remember, last time I tried to get you to think about how to do this in a working fashion. And the way I asked you to think about it is you would draw a line parallel to whatever axis you're going to integrate with respect to first. And maybe draw a couple of lines just to make sure that you're going to be hitting the same functions going in and going out of the region. So if I look at this line movement here and I go into the region at some function that looks like this function over here, I would have to figure out what that function is. And since I am integrating with x, I want to figure out what that function is where x is isolated by itself. X is the explicit function of y. So this going into this function, I have to identify this function from the equation of the relation between x and y that describes that region, and I want it in terms of x. So if I take this equation and solve for x and realize that these x values are negative, I must be looking at the negative square root of 4 minus y squared. If I solve for x. What? Oh, because these are x values that are on the negative side of x. Is that? Oh, okay. Any other questions? And then as I move along, I would be inside of the function until I get out, inside of the region until I get out of the region, and I get out of the region on this function. which looks like it's still that same circle, except it's on the positive side of x. And if I, again, solve for x here, I would get the positive part of the square root. Okay? And then my y limits would be from what to what? What? Negative 2 to 2. I'm glad you didn't try to solve for y here and look at the top half of the circle or the bottom half of the circle. Because if we did, we'd have y is equal to the square root of 4 minus y squared, right? Plus and minus. But that wouldn't be appropriate to put here because they both have to be, the outer limits have to be constants. So this is our valuable set of inequalities that's going to help us write our double integral, our iterated integral. And remember that you have the square root of x squared plus y squared in the integrand. And now here we're deciding to integrate with respect to x first. So I'll say dx, and then I will write my x limits. My x limits go from negative square root of 4 minus y squared to positive square root of 4 minus y squared. And then my y limits, when I write dy, I can fill in my y limits now from negative 2 to 2. Yeah? Sure. There's no specific reason aside from somebody said x. But yeah, we could have totally done this the other way. We also could have just took a quarter of the circle, right? And since the shape of this volume looks like it's symmetric, if you just take a quarter of the circle, then multiply your result by 4, that also would have worked. But I wanted to do things the hard way. I'm not going to integrate this. Are there any questions? Yeah.
If you were that in the
At least, yeah, and some other stuff happening too. If I were to do it, I'd plug it into Mathematica. Yeah. For serious?
When I actually go back to my notes and are you likely to make us do a problem like this on test?
Not like this. Oh, so if this was me, I'd go to section 15.4 and do it that way. What? What's that mean? I'm pretty sure. Do we want to go there? What? Where am I? Okay. X, Y. Good luck. Oh. There's no earth here because it's a definite integral, so you can actually put values into the earth function and get results.
Let's try to solve for the
Okay. So let's stay on this page, and what if we wanted the actual volume of the cone? How do we set up our integral? It's almost like what we have set up right now. Negative space? How's that? Close, yeah. Well, no, that would work. Not close, but that would work. Actually work. But I want to set up one integral to do this. You guys heard what William said, right? He said just find the volume of the cylinder and take out that thing that we just found, and then that you get the correct answer. But in terms of setting up the integral, yeah.
Take that upper limit, whatever it is.
Yeah. So we didn't talk much about this yet because this falls under the category of, they call it applications. But what we really have here in terms of this cone are two surfaces. We have a top surface, and let's say this goes to a radius of 2, right? And so you would imagine this would be a plane, z is equal to 2, on top. So you have a function or a surface z is equal to 2, and then you have the surface of the cone z is equal to the square root of x squared plus y squared. And you will be integrating this over the same region that we have described here in 2 dimensions, except instead of going from the cone down to the xy plane to 0, you're going from the plane, I guess I should say, from the cone to the plane z is equal to 2. So then this integral here would have the same limits but your integrand will be a difference between two surfaces. So you have z is equal to 2 as a top surface, and then you have z is equal to the square root of x squared plus y squared as the bottom surface. So if you calculate this, then you would get your result, which should be the same as what William said when you find this cylinder, volume of the cylinder, and take away that volume that we took out.
We actually found the volume.
I don't know what to do to convince you. We could actually find this, and you guys know the equation of you know how to find the volume of a cylinder? Okay, so once you guys think about the volume of a cylinder, meanwhile, I'll ask Mathematica to compute this integral that we just wrote. So again, what was the volume of the cylinder? Did you guys figure it out? I want the actual volume. Just tell me. 16 or 4 pi or something? It'll be what? So it'll be 8 pi. Height 2, radius 2. Times the height 2. So 8 pi. And then we take out the 16 pi over 3, and we get 8/3 pi, which is the... Okay. All right, so now to do this by hand would probably require some trig substitution and then a little bit more stuff, fancy stuff. And so you can see it's a little difficult to think about it that way. So do you remember in Calc 1, at the end of Calc 1 and most of Calc 2, when we found it kind of difficult to integrate something? What we did was we tried to transform this into something different so that we can manage it better. So now we can actually integrate it if we move to a different domain. So you can think about this as the x world. And what we do is we go into the u world. So that we can actually perform the integration. And what we did essentially is we simplified our problem. So there's something equivalent when you go to multiple integrals and we're working on something like this. Actually, I think a better example might have been the actual trig substitution. Anyways. So where we are currently is we're in a Cartesian world where things look a little bit difficult to deal with. But what we can do is, with a proper substitution, we might be able to go to a different world that would make things a little bit easier. So I'm going to put d star here. And then I'm going to change my dx, dy into some other d something, d something. And those two somethings will represent the new world that we're going into. So in this old world that we live in, we have this circle. So what would be an appropriate world to move into if you're dealing with circles? Polar coordinates. What are the variables that they use for polar coordinates? R and theta. So maybe, somehow, if we move to this new polar coordinate world, it'll be easier to deal with. Now, in calculus, I guess this is still calculus. Back in Calc 1 or Calc 2, we did the U substitution where we let U equal to something. So there was some substitution that happened there to go from the X world to the U world. So similarly, we're going to want a substitution of some sort. And since you guys actually mentioned polar coordinates, do you remember what the substitution was for polar coordinates? There's more? There's more? What? I'm getting impatient. X equals R cosine theta, Y equals R sine theta. So we got a pair of relationships that allow us to move back and forth between worlds. So we are going into polar world. I'm just making that up. It does, doesn't it? It's always funner to get out of reality once in a while and go to a different world. Yeah?
So this can be used for tough to integrate?
Generally, this could be used for tough to integrate, but specific tough to integrate. And yeah, so this would be ideal for regions that are circular. That can be best described with polar coordinates. Okay? So let's take our example of this circle where we describe the circle as x squared plus y squared is equal to 4. Actually, to get the whole disk, you say less than or equal to 4. But the circle itself is really what we're looking at because it's the boundary, right? So the circle is x squared plus y squared is equal to 4. Now, how would you describe that in polar coordinates? This is back in chapter 10 now. If I wanted to draw a circle and I wanted to do polar coordinate circle, what would my equation be? Yeah? R equals constant. So in this case, the constant is 2. Now R equals 2 just kind of gives me this outer part of the circle. Oh, wait. When I just say R equals 2, I kind of have to be more specific, right? Because if I do that in my graphing program and just say R equals 2, I didn't want to draw a circle right away. What I'm trying to say is that if I say R is equal to 2, I can really be specific as to how far I want this to go around. Like say, if I just want this to go around halfway, then I would tell my theta where to go. Right? So if I want the whole circle, my theta would go from 0 to 2 pi. So that will help control my circle, right? Now, if I was just graphing this, if somebody just told me, okay, here's a theta and here's a r, theta goes from 0 to 2 pi. And then r went from, well, r is equal to 2. It's just a line where r is just equal to 2. But I really want to shade in everything in here. So what can I say about my r? So r is going to go from, so r would go from 0 to 2, right? Yeah. Well, let's think about that back in the real world. Let's say that somebody was in the polar world controlling somebody in the real world, and they say, let's let your r go from 0 to 2. And so if you let your r go from 0 to 2, well, we don't know anything about theta, so let's assume theta is equal to 0. Theta is equal to 0 is just a positive x-axis, right? And somebody says r goes from 0 to 2. We can think about that as a little strip on the theta is equal to 0 or the positive x-axis. Now, if somebody says, now let your theta go from 0 to pi over 2. Let's start with that. So you would imagine these line segments with angles ranging from 0 to pi over 2. And then if you go all the way up to 2 pi, then that would be everything else. That would describe the whole disk. Say that again? The rectangle just gives me a set of limits in my polar world. And what we're trying to do is we're trying to relate that to what's happening here. So actually, now that you ask about that, gets me thinking about something more interesting to represent. These line segments that are being drawn here can be associated with these line segments that are being drawn here. Cute? It is, huh? I don't know. This thing. Not only that, but if I draw lines that are parallel to the theta axis, let's say theta was equal to, oh, wait a minute, did I do that right? Yeah, okay. So if I say r was equal to if r is equal to 1, we know that that's a circle of radius 1, right? And then we can draw a couple more lines here that would represent circles of different radii. Too much? Okay. We good so far? All right, so it looks like we can make the substitution where x is equal to r cosine theta and y is equal to r sine theta. There's just one more problem. Back in calculus, Calc 1, Calc 2, whatever, in the old days, when we change variables, there's a differential that takes place. And we need to replace this dx with something else. Or we want it in terms of the new variable, right? And so we say, oh, we're going to take the derivative of something. And then when you do take the derivative, you come out with this extra differential. So this is an extra integrating factor that we need to worry about. Now, that integrating factor that we need to worry about comes from taking the derivative. If you just had u is equal to x squared, easy, that's just the derivative, right? And then you'd find x and you'd solve for x or whatever else you need to do. But unfortunately here we have two variables, x and y. Not only that, we have two variables in the real world and then two variables in the polar world. So we're going to need to deal with the derivative in a different way. So how are we going to deal with the derivative? Well, let me introduce you to the Jacobian. The what? Jacobi. I forgot his first name, but his last name is Jacobi. This is the Jacobian. And the Jacobian allows us to find a, quote, derivative. Now, since we have two variables in each of them, we have to be dealing with partial derivatives. And so the notation for this is a partial derivative of your real world variables divided by the partial derivative of your new world variables. And in general, we're going to want just a positive representation of this, because in linear algebra, I don't know if you know, we're going to be taking determinants. That's why I mentioned linear algebra. In linear algebra, when you take determinants, if you switch rows, the determinant changes signs or some weird thing like that. And so what we want to say is it doesn't matter if we integrate or take the derivative with respect to r first and theta, so the order of these things don't matter. So we're just going to want the positive representation of this. And so we're going to want the determinant of a set of derivatives. Now, there's two dependent variables and two independent variables. So how many derivatives do you see here? 4 of them, right? So the x and y are the dependent variables, and the r and theta are the independent variables. So give me one of those 4 derivatives. Partial of what with respect to what? No, because we want x and y are both dependent, and they're dependent on r and theta. Partial of x with respect to r is one of them. Partial of x with respect to theta is the other one. Partial of y with respect to r. Partial of y with respect to theta. So this is your Jacobian. And then you find the determinant. Remember how to find the determinant? You add these two, and then you multiply, you subtract these two. Remember that? No, it's not quite a cross product, but yeah, there's some cross producting involved. Yeah, so multiply the diagonals here, and then multiply the, they call it the wings, and then subtract that, subtract the wings. All right, so polar coordinate transformation is a specific transformation. Yeah? It turns out that because we're going to take the absolute value, it's not going to matter.
But if it were the other case, then we would have to take the order into consideration.
Yeah, but we're not worried about that. We're not going to worry about that. So the Jacobian for the polar coordinate transformation, it's specific because we know x and y. Right? So let's actually find it. And after we find it this one time, you don't ever have to look for it again, because it's always going to be the same for polar coordinates. Now, if we do a different transformation, then you'll have to redo the Jacobian for that. So derivative of x with respect to r looks like it's just cosine theta. Derivative of x with respect to theta looks like it's negative r sine theta. Derivative of y with respect to r is sine theta. Derivative of y with respect to theta is positive r cosine theta. So multiply the diagonals, you got r cosine squared theta minus multiply the wings, you get negative r sine squared theta. And if we factor out an r and then do that sine squared, cosine squared, you're going to get r. So whenever you do a polar coordinate transformation, don't forget the r. Okay? Now let's go back to this page, and then we'll start another page. These are the integrals that we're moving towards. Right? And we just found this integrating factor here, which is r. So let me summarize that over here on a new page to say that polar coordinate transformation, let's type this up. Whenever we do a polar coordinate transformation with double integrals, we're going to write our integral the same way we've been writing it, and when we see dA, it's assumed to be in Cartesian coordinates, dx dy or dy dx. But we're going to get specific here when we do polar coordinates. And so now I'm going to put d star to say that our domain is different now. Right? It's r and theta. our f, now instead of xy, which is what's kind of implicit in this in this left side of the equation, instead of xy you have r cosine theta and r sine theta. And then r, your Jacobian, that's like your, when you take the differential in single variable calculus, when you do u substitution, there's an extra thing that pops up. And then you have dr d theta. And I'll put dr d theta here, but you might be flexible in switching the order if you need to, depending on how you write your limits. Okay? So I know this sounds funny, but always remember r dr d theta. R dr. R dr. I can't put another r there because then it would be wrong. So just r dr d theta. Don't forget your r. So this is as important as saying the constant limits, or the limits for the outer integral is constant. Don't forget the r. The Jacobian, it's like this, when you switch variables, it's like the derivative. No, just because of like a substitution. In this case, it's a u substitution. Remember, trig substitution, you do the same thing. You say x is equal to sine theta, and then when you change a dx, you change that with a derivative of sine theta. So the same thing happens with whenever we do any sort of substitution. We always have to consider the derivative of the function substitution that we're doing. And so that's what we're doing here. To figure this out, we need the Jacobian. Jacobian to the rescue. Okay? We can kind of think of this as a Jacobian also, but it's a Jacobian for one dimension. And this would be the Jacobian for two dimensions. And we'll probably see a Jacobian for 3 dimensions. All right? Now, let's go back to this problem that seemed like it was really hard. Well, it wasn't hard because I just put it into Mathematica. But if you were to do it by hand, it seemed like it would be kind of difficult. We did some of the legwork for this already. So let's just recap what we've done. This is D. We got some complicated limits. You don't have to rewrite this over again. Got some complicated limits for D, right? We got the function, f of x is equal to this thing. Right? And then our integral looked really messy. Especially if I write it really messy. Right? So, when we did our transformation, things happened. In fact, we wrote the inequalities for this already, right? R goes from 0 to 2, theta goes from 0 to 2 pi. We also noted, or according to this, we're going to put in x is equal to r cosine theta, y is equal to r sine theta. But we also have this other relationship to say x squared plus y squared is equal to r squared. Remember that? That was one of the things written on this page right here. Right? So let me jump to saying our f function now is this function where, hey, I'll just replace x squared plus y squared with r squared. And that's just r. R. Now I want to replace my dA, my dy dx, with what? R dr d theta. Now let's take a look at the limits again. Limits with respect to r. R is first, so r is going to be the inside. R goes from constant limits. Look at that. Theta goes from 0 to pi. Now let's match all these things up. Right? And then our d that turned into d star, instead of d being a circle, we have d star as a rectangle. Not only that, whenever we're dealing with rectangles, we have constant limits. Hey, remember what happens if we had constant limits? We could separate them. There's no theta. Well, we could pretend that the integrand for theta is 1. And then the r is just a couple of r's being multiplied together. That's 2 pi. This is r to the third over 3. And we put 2 in there, and then we put 0 in there. And what do we get? (16 pi over 3). What was that? That was the answer that Mathematica got for us. But look, Mom, there's no Mathematica. Yeah. RDR. We're done. Have a good weekend.